Sami is he's a senior director of machine learning research at Apple since 2021. His research interests span areas of machine learning, such as deep architectures, representation learning, vision, and language processing, and more recently, reasoning. He co-wrote the well-known open source Torch machine learning library. And with that, I welcome Sami Bengio. I hope, since you worked also with vision, that you won't neglect the question of grounding when you talk about reasoning.
Thanks, Stephen. Thanks for inviting me. It's good to come back to Montreal, where I've been for 25 years or so. First check, do you hear me in the back or do I need a mic? All good? So I will try to tell you why I think even with the biggest LLMs that exist in the world, learning to reason remains and will remain hard for some time. Let's see. Oh, okay. So let me start by trying to explain from my point of view what is reasoning. So reasoning is the action of drawing conclusions efficiently by composing concepts that you already know. So here are a few examples of reasoning. Some of them are more or less hard, even though they all look the same. Suppose you are given, you are given these input symbols, and you have to classify them into ones or zeros, and you have to find the pattern that makes it ones or zeros. And the pattern that you should see here is that when the two symbols are the same, it should be 1. If they are not the same, it should be 0. So what you see on the left is the training examples. You have to try to come out with the reason of the solution. And on the right, I'm giving you examples that are more or less difficult to actually solve. So you can see a pair that you've never seen, like the two square. You've never seen the two yellow square on the left. You can see new symbols that you've never seen on the left, like the star. You've never seen it. You can see a different number of input, like 3 symbols instead. But the rule is basically the same. Once you understood it, no matter which symbol you use, no matter how many symbols there are, and no matter new combinations of symbols you see, should always be the same. So the idea of reasoning is that you can come up with solving problems you've never seen before just because you're putting together concepts that you learned with the training examples. And it's very different from memorization, where you would just put all the examples you've seen in a big memory bank and get out with solving similar problems. So usually the main trademarks about reasoning is 2 things. One is extrapolation, and the other one is efficiency. So extrapolation means that the examples you are going to see during test or at inference when you want to use the model are going to be different from the distribution that you saw during training. And this is about reasoning because since you're out of the distribution, you'll have to find ways to compose from the examples you've seen in the past to try to solve problems that were completely unseen. Even the distribution of them wasn't seen. It's also about efficiency because, in fact, if I gave you like a combinatorially more example of training, you would be able to solve it, but that would need so many examples at a time that wouldn't be efficient. So it's really about these 2 things. Why is it challenging? Well, because in the days of LLMs, we can see how the models that we train are bigger and bigger. So they actually have more and more capabilities of memorizing everything you tell them. And indeed, they do. So because they can do that, they can easily come up with a simple solution that is just like a nearest neighbor of one of the training examples you've seen. But that might not be the right solution to do. And obviously, you could say, well, I'm going to get a bigger model again, and I will use more GPUs, but at some point, you won't be able to solve it. So if we can be smarter instead of just getting more data, that will be useful. In many problems, like arithmetics or algebra or some kind of reasoning or planning, there's basically no way you will get enough training example ever to really be able to solve these reasoning problems if you didn't understand the actual simple combinations of rules that we need to apply. So I want to give you a few examples of the fact that it's even now hard. In a recent paper from people in my team, they looked at visual reasoning. So look at the graph on the left. So you see this grid of 9 symbols, and you're asked what is the bottom right symbol that should be there, and you have 6 options, and you have to find how they are connected to each other, and that's the visual reasoning part. And it turns out that it's very hard for an LLM. So Gemini Pro, GPT-4V, all these large models that you've heard in the press or anywhere else you're using your news feed, they all fail to these kind of examples. So there's basically no good LLM that can succeed. Something like that humans can usually solve. So that's one example. Let me give you another one. It's the parity. So let me explain first what is parity. You're given a number of symbols, or a sequence of symbols, of 2 kinds of symbols. Here in the example, you have a yellow square and red triangles. And the problem of parity is to just tell me whether there's an even or odd number of triangles. Okay. It is actually a simple problem. If you understood it, you can solve it very quickly. Now, what will be difficult is that at training time, we only show you example with a fixed number of, or at most, say 20 symbols of input. So there will be no more than 20 square and triangle total. And at test, I'm going to show you longer sequences. But the algorithm remains the same, and you could solve it if you actually understood what was the question. You could solve it no matter how many symbols you see at input, because you just need like a 1-bit memory in your mind to know whether you've seen an even or odd number of these triangles, and then you can solve it. It turns out that it's hard for LLMs. So on the left, I show an example where you see the gray part is the number of symbols that were seen during training. So the model was trained and saw between 10 and 20 symbols. And the different curves you see is the performance of different models of different sizes, from a few millions to a few billions parameters. And you can see that when the test examples are about the same length as the training examples, the accuracy is 100%. So it understood. As soon as the number of inputs grows longer than 20, you can see the curves going down very quickly. And none of these models, even the bigger ones, like the 64B model, which are like in the big size that we see today, they all fail very quickly. There are many ways to improve that. One technique is called the scratch pad. Another one is fine-tuning. I won't go into details, but even these techniques fail. Sometimes they fail a little longer after, but they do fail. So something is wrong. That problem is not that difficult, but you can see how the model actually was able to understand something very restricted that was conditioned on the length of the input sequence. It didn't really understand the concept of parity. It understood a very restricted set of parity. So I'll give you this morning 2 vignettes about why it's hard, and we'll see where that goes. So the first one is a paper from last summer at the ICLR, one of the big machine learning conference. It's called Generalization on the Unseen. Oh, and I don't know how it works, but I think you can ask questions whenever you want. Is that how it works?
If that's what you wish.
Yes. Yeah. Feel free to ask questions when I when I'm not clear, but I don't always know the level. So let me start with an example that will be similar to the parity one I showed you. Here, the example will be you have to learn the majority target for 3 voters. So there are 3 people, X1, X2, and X3. They can either say -1 or 1. They have only 2 things to say. And each of them will say something, and you just need to learn the majority function between the two. So which of the 2 symbols do you see in a bigger quantity? That doesn't sound difficult. But of course, I'll make it a bit more difficult. So first, it's a very restricted problem. It's just an example. There's only like 8 examples that you can see. They're all here. That's the totality of the training set. But to make it a bit more complicated, while training, I will always hide examples where both X1 and X2 vote -1 together. So examples where -1 for X1 and X2 are hidden. Yes, so these two, I will call that the holdout or the unseen. So during training, we never see these 2 things. You have to make your mind about that. So you can see all the other ones. You can see the training set, which are all the other ones. So now, given that situation, there's actually many solutions that can fit that problem. And you can characterize all the solutions that can fit the training set with the actual real solution, the majority, whatever that function is, I'll get back to it, plus a term. And that term, you see this delta x times 1 minus x1 times 1 minus x2. And I've put that term because it's interesting. Because x1 and x2 are never -1 together, there will always be one of these 2 terms at training that will be equal to 0. And so at training time, the term on the right, the delta x times something, is always equal to 0, which means we don't care about delta x. Delta x is a function, and whatever delta x is, the solution will be majority. So there are many solutions that will fit the training set. They are all of the form, the actual solution you want, plus a term, and that term can be anything. And the problem is that we don't know which one the model will learn. It can learn any of these ones. And, you know, what is an LLM? What is a deep net? What is a neural net that will be trained on stochastic gradient descent? Which one will it choose? Well, I said that. That's so what I'm going to show in the next few slides is that we have characterized which one it will learn actually for real. And it's called a solution that will be biased towards mean degree. Let me try to explain what that means. So when the inputs are just -1s and 1s, and we're only talking about Boolean functions, where the output is also -1 and 1, all these functions can actually be expressed as polynomials. So of the form, you know, some function of x1 plus x2, product of them. This is the kind of functions you can express. And the majority is one of them. So it's just the sum of the terms, the plus minus the product of the 3 divided by 2. Turns out this is a polynomial of degree 3 because of the last term. There's a product of 3 terms. That's what it means. And what we showed is that if there are many solutions, the one that the model will choose is anyone that has the lowest degree. So a solution where all the terms are the smallest. And in particular, there's one of degree 2 that fits the training set. And that's the one that the model will fit. And that's sad news because it means it's not going to learn the majority. It's going to learn something else, this term on the right, no matter how you do it, no matter how big is your model. All right, why is that important anyway? Well, it's important because it's basically at the basis of reasoning problems. Most reasoning problems will be in this situation where you have access to a training set and it's incomplete because it's impossible to have a complete view of all possible combinations of symbols when the number of symbols is large, because it's combinatorial. So quickly you have more of these combinations than the number of atoms in the universe, and you'll do. So you're always in the situation of what we call out-of-domain generalization or extrapolation. So there are many places where this happens. I already said that. So I'll try to explain how we come up with our finding, which is that we now understand which solution the model will choose by making it as simple as possible. And we developed this framework that we call generalization on the unseen. We're going to make it as simple as possible by saying...
I have a quick question.
Oh, quick question, yes.
You left out the -1, -1, -1 case.
Yes.
Can we assume in any learning example that somehow intuitively it knows that you don't have to worry about that case?
That you don't have to worry. You cannot assume. That's the problem is that we don't know what the model will, and that's what we're trying to understand. So we cannot assume anything, though. It's just it's like saying I've never seen images. I've seen images of dogs with the sun, but never with the rain. Does it mean that there will never be rain?
Yes, but your conclusions about the difficulty of reasoning of neural nets are based on this particular, in this example, with a constraint on the sample. It's saying a condition on the sample.
But you don't know that's constraint. You only see the examples. I know because I see everything. But the model sees examples. It doesn't know that there's a subset, that there's a mathematical formula that explains which subset it's going to see. It's just...
And the general conclusion still holds, which is that this is true about reasoning in general and not on this particular...
Because exactly. The reason it's true is that when you reason with symbols, so these are, discrete things, they take discrete values, there are combinations of these symbols that you will never see at training time because there's too many of these combinations. It's impossible to see. And so you can easily come up with an example where you will have like a set where you're missing some combinations. You still have to be able to do something about that. We humans don't need to see the combinations. We have a way to, we have what I would say a regularizer that tells us we need a simple solution that explains what I've seen. And the problem is that what we mean by simple is not what the neural network means by simple. Yeah. There are many definitions of what simple is. That's what I've been trying to explain. The model has a definition of simple that doesn't align with our definition of simple. And maybe we can fix that, but today it's not fixed. So here's how we came up with this solution. We're going to consider any problem where you are there's a domain. So the domain is all the possible combinations of input that your model can see. And during training, the model will be able to see any combination of inputs from part of the domain and none from another part of the domain. And it doesn't need to be anything that you can express, but there is a part of the domain that you will never see during training. And the question is, how are you going to do if I now show you an example in the part of the domain that you have never seen during training? So you see, it's the same idea as I proposed in this simple example, but now it's more generic. And the question is there any hope whatsoever that we can learn a model that will solve any of the questions that will be given in the unseen part of the domain? And as I said, I think the solution is that you need some prior, you need some ways to simplify, to regularize your solution so that it goes towards the solution that you care about. So quickly about these functions, because we're looking at a very simplified problem, we wanted to be able to simplify the setting of combinatorial problems, which are usually of discrete nature, and there are many combinations of them. So the simplest version of that is when you have two symbols, so it's Boolean, and you can combine them, say with like a polynomial, so a combination, a sum of monomials. And so that's what this equation is saying, is that all the solutions that we're going to be able to provide are just sums of weighted product of your input values. And so in this sum, you have the coefficient, which is the weight you put for each of the terms, and then you have how many terms you are multiplying together. That's what a polynomial is. Nothing dangerous about that. And now I recall that if you are in this setting, there's set of combinations of the input that you will not see. That's what we call the unseen. And from that set of combinations, you can always write the solution as the right solution, f of x, plus an arbitrary function times the product of all the combinations that that will happen. So in this case, it's you've never seen the variable x1 equal -1. So you can always assume that at training time, it's always equal to 1. So 1 minus that will always be equal to 0. So any delta x from this set of function will fit your training example. That's the same idea as I already proposed. Good. I need to tell you again what is the degree of a function. So if you have a polynomial, you can look at like the number of terms that are multiplied in each of these terms, and that's the degree. So in the first part, you can see that the degree is going to be equal to 2 for both of them. Good. Won't go into the details of the degree profile. I think it's not very interesting, but there are going to be many solutions that fit your solution, some with lower and some with higher degree. I won't go into that details. It's not very interesting. But what we showed in this paper, there are 2 theorems that are interesting. And of course, I'm not going to give any details about these theorems, just to give you the high level of them, is that for very simple neural networks, and here I'm saying neural networks that no one uses, but that we can actually study. Here it's a random feature model where the first layer is just a random projection, and then you can learn the second layer, and that's all you have. So a very restricted set of functions. In this case, you can actually show what I said. When the model has multiple functions that can fit the training set, it will choose the one with the lower degree profile. How interesting is it? Not that much, because that's not a function, that's not a model that anyone is using, but it's good that you can prove it. Now, what we showed now is that it also works for other models like linear functions and diagonal linear neural networks, but it also works empirically. So just using experimental experiments, that it also works for transformer. Now, transformer is the class of function that everyone is now using to train their LLM. So if you've heard of LLMs, you've likely heard of transformers. And that's a much more rich and complex set of functions. But it turns out that we obtained the same result empirically than the ones that we showed on simple functions. So again, we showed it on simple class of functions, but it also seemed to work on the much more complex class of functions that are actually used for all these big LLMs. So let me show you the kind of very simple experiments we did. So here in this example that you see, there's a target function. It has 15 input variables, x0 to x14. But the solution that you're looking for is just the product of the first 2. Yes. All the other inputs are not used, but you don't know that, of course. And more than that, you never see the 2 variables, the first 2 variables equal to -1 together. During training, you never see that. But you can see that there's plenty of examples you can see, because there's all these distractors, x2, x3, they are never used. So at training time, again, 1 minus x0 times 1 minus x1 is equal to 0. So you can have any function that uses that product of term, and all of them will be compatible. What will happen now when you train a model? So on the left is this random feature function, that family of functions that we train. The graph that we see, I have to explain it. On the x-axis, it's the training time. Epochs is the training iterations. On the y-axis is the actual value of the monomial that we're going to show. So let's look, for instance, at the term x0 times x1. It's one of the term of the function, and the value of the coefficient is around 0, as you can see. So there's no x0, x1 in the solution. Instead, you can see that the term in x0 and the term in x1 goes to 1. So there's a term in x0 in the solution. There's a term in x1. And there's also a term in in 1, which is actually -1. So the solution that it finds is x0 plus x1 minus 1, which is compatible with the training set, but it's not the function that we're looking for again, because that solution is of degree 1, while the one we're looking for is of degree 2. Same for the transformer, you get the same thing. The curves are slightly different, but it's actually the same solution. Not going to show, I mean, neural networks have some bias. I won't go into details about this. Let's see, there are other functions, but I think you got the point. Where do we go with that? Let me go back to one of the functions I said was hard to learn, and that's the parity function under the length generalization concept, where you learn parities with a given number of length of your input, and then you're going to test it with longer sequences. So it's actually a hard problem, as I said, weirdly. The actual solution is just going to be the product of the input values. If they are -1s and 1s, you can see that you retain the sign, and that's good enough to solve the problem. So it's a very simple solution. But of course, it's not going to work that easily. In fact, we can show that given any training set you're going to get of a finite length that is smaller than the total length, you are going to find a solution with a lower degree profile. So there will always be a simpler solution, simpler according to the model, and that's the one that it will choose. So you will never find the right solution. And more than that, you're going to make a mistake that is combinatorially big. So as the length of the test example is longer and longer compared to the training examples, you are going to make a bigger and bigger error in the model that you're going to find. So this is pretty bad news. And that's showed by the examples that I showed you, where the curve goes down very quickly. That is explained by this solution, unfortunately. I won't go into that. I don't think it's useful. But so the first part is pretty depressing in a way. No matter how big your model is if the problem you want to solve is this kind of reasoning problem, where the number of combinations of your input grows, and you will never see enough of these combinations at training time, you will get into a solution that has the wrong bias, that will go to a solution that is simple according to the model, but not simple according to you. So where do we stand with that? I think we need to think more about how we can put in our models some priors that will favor things that we humans do naturally, like symmetries, like how we compose things, how we come up with simple solutions. So these are not always easy to come up with. So more work for us. Let me go to the second part. And if you actually have questions on the first part, maybe time to do it.
No, there are none on the spectators yet.
Okay.
Any here? Well, either they're following you faithfully or they're completely lost.
Perfect. Not perfect. Perfect for the first one. But okay, well, let's move on to a different study. And the question now is, what algorithms can transformers learn? So again, transformers are this class of functions that are used at the heart of most modern deep learning approaches, including large language models, but many others. And so the question now is, what can we learn with that? And again, I'm going to go back to this length generalization problem, because it's actually richer than I thought at first. And so this is a paper that we presented at ICLR, that's another machine learning conference, this spring. All right, so again, we're going to consider the same class of functions where you have discrete symbols, and you need to do operations on them, sorting them, adding them. Again, you can see how in some of them there will be combinatorially different solutions. And for each of them, you're going to be able to train them all with the training set and then look at what happens on the test set. But again, during training, we are going to see examples of a given length. And here to make it simple for addition, for instance, for additions of 3-digit number. And then at test time, we're going to show it problems of longer length. In that case here, 5-digit addition. So same setting as the previous paper, but we're going to look it from a different angle. So that I already said. And you remember I already showed the graph on the left about the parity that was hard, even with all the novel techniques that exist, like scratchpad and fine-tuning and all of that. Even with the biggest model, you will struggle to solve this length generalization problem in some tasks. I showed it on parity on the left, but there's many more problems of this task. Here, it's another problem called variable assignment. No need to go into the details of what it is, but the class of problems that will have this length generalization problem is actually bigger than we think. So that's not just parity. So let me start with a simple example, which we call the counting task. So this is like a completely made up task. It's not necessarily useful, but it's interesting to study it. I give you two integers, A and B, and your task is to just output all the integers between the two. So if I give you 5 and 8, you have to say 5, 6, 7, 8, then the symbol for I'm done. Now, that sounds easy. At training time, I'll show you like as many examples as you want of this A-B pair, but the difference between A-B will never be bigger than 60. So 5 and 8, the difference is 3. But I will never give you 1 and 100 because the difference is bigger. At test time, I'll show you bigger example, longer. So the difference between A and B now will be between 60 and 100. Will it succeed? So that's the question. And the answer is yes. So now that there's a weird thing. The parity was not succeeding. I show you examples of where it was not succeeding. But on this case, it is succeeding. So what's different? Why it works on some, doesn't work on others? That's the question. So let's try to understand what a transformer is doing. So what a transformer is doing, usually, I won't go into the details of what's in this box, but the way it works is that you're shown a sequence of symbols. Here, you're shown the symbol 5, 8, greater than, and then maybe 5 and 6, and you have to output the next symbol, 7. So to output 7, you saw all the previous symbols. And the function that you're looking for is a function that if I show you the first 5 symbols, will output the 6th one. Here it's 7. But if I show you the first 8 symbols, it's going to output the 9th one. And I think that's the interest. The same function, the same transformer, no change in the function, is able to work on the left and on the right with different length, and it works on both. So that's what the transformer is doing, at least. The question is, if I was to write a program that actually solves this problem, where I'm given a sequence of symbols of variable length, and I have to, output the right symbol after that, what would be the code that I would write? So if I was to write it in Python, that would be the thing on the left. You don't need to understand it, but it's a very simple code that does not depend on the length of the sequence. It just says, well, I'm going to look at the last symbol. If it's this, I do that. If it's this, I do this. It's like a 5 lines of code. And you can apply this program, and it will always work for any symbols, for any input that you showed it. So that's cool. If we knew that the transformer is going to learn that program, then we know that the transformer will work for any sequence. Because that program doesn't care about the length. It just cares, it just applies the same formula no matter how long the sequence is. So that's good news. There are solutions that work no matter how long the sequence as input is. The question is whether a transformer can actually be learned that will exactly encode this thing. So can the transformer represent this program in particular? Because if it cannot represent this program, there's no way it can learn it. And if it cannot learn it, it's not going to solve the problem you want. So first question is there a way to change the parameters of the transformer such that it actually encodes this function? If it does, cool. So we came up with a conjecture that if indeed you can show that there's a program that can be implemented that represents the function you want, and it can be implemented in Python, and it's a simple program, and you can show that the transformer can actually learn it, then it will learn it. Now, it's actually not in Python. It will have to be in a very simple language. And we actually found some other people from about 3 years ago who wrote this language they call Rasp. And it's a simplified version of Python. Think of Python with a much simpler set of functions that you can use. In particular, there's no loop. It has to be, you see the whole input and you have to apply a simple function to all of the input at the same time and things like that. So it's a simple language, simplified language. And it basically looks like that. On the left, you have think of the transformer, which has layers. And for each layer, it takes the input and it transforms it into the output, which becomes the input of the next layer. That's just basically what any neural network is doing. And the idea of this language, Rasp, is that for each of the layer, it will apply one of the formula of the language. So each layer of the transformer is equivalent to one line of code of this simplified language. And if you can show that you can implement that such line of code in the parameters of that layer of the transformer, then you can indeed implement the program that you want to implement in total. So we simplified even this Rasp because it was too expressive. We made it simpler, and we call this Rasp-L so that it's something that we think can be learned because it's simpler. And then we thought, okay, so we think that if there is a solution in this Rasp-L language to implement the problem that you want the model to solve, then the transformer will actually learn it, and it will generalize to any length because it actually learned the right program. So I said that the problem of this language is that it cannot implement anything. In particular, it cannot implement parity. And we said actually parity is hard. So it's kind of a good news. It cannot implement parity, and we know it's impossible. So it goes into our intuition, and in fact, that's our conjecture. If you can implement the problem you want at hand with this very simplified language, then the transformer will learn it, and it will work and generalize to any length. So we have not proven this thing. So it's only a conjecture, but we tried it empirically on many, many tasks. And here I'll just give you a simplified version of that. So here are just like 7 tasks, counting, the mode, copying in some way, sorting, adding, parity. And for each of them, we actually tried to write the code to see whether we could actually solve it. And the left are all this simplified tasks for which we were able to write code in this Rasp-L language. And on the right are all those for which we were not able to write the code for this language. And then, well, we tried it. We generated as many examples as we wanted on the task on the left and on the tasks on the right. And for each of them, we did the same idea. We trained on problems of a given length at most, here 40. And then we tested on problems of a longer length, here 50. And we looked at the results.
Should that be Rasp-L-able?
So that's oh yeah, it's Rasp-L-able, yes. Good point, totally, yes. And here are the results. kind of agrees with our conjecture. All the problems for which we found the code that could be written in this Raspberry language, the test on longer length provided 100% accuracy. So it actually learned the function no matter what the length was. All those for which we didn't find a Raspberry implementation, including parity, it failed. So for parity, the answer is 50% because it's a coin flip. There's only two options. But for bigger problems, like addition, it actually fails completely. So that's kind of agree with so we cannot prove that this will always be the case, but we have a strong intuition that this will be the case. Actually, in a different paper, we showed that it is going to be the case in some restricted sense. That I'm not going to go into the details. Yeah. So transformers is this class of functions that is very rich, but nevertheless cannot implement anything. Or, I mean, it can, but it might not implement the thing we want. In particular, it might not generalize to longer length if indeed you cannot represent the functions that you're looking for in some very simplified language. So I think with that, I'm done.
Okay. Some questions are already coming in, but first we'll have Gary.
Remove. Oh, yes, so
Gary.
Where's Gary? I'll let him go. Yeah.
Gary Littwin will be speaking tomorrow, but he's going to discuss it today. You want to come around this side so they see you?
Sit here. Is that mine? Yeah, I should just put it.
Yeah, I think so. Okay. All right. So I
Without yourself.
okay. So that works. All right. Great. Okay. Thank you, Sam, for that talk. And thanks for sending me your slides last night. I wanted to touch on 2 points from your talk. And I'm going to focus on some human data that you and others in the in-person virtual audience may find interesting. So I find this work fascinating, and my training is as a cognitive scientist, as a connectionist cognitive scientist. For most of my career, I've worked with people with running experiments of various kinds on people, specifically looking at the role of natural language in augmenting human intelligence. And so what strikes me looking at these points, the question kind of naturally arises to me is, to what extent is this also true for people? To what extent do people need to be nudged in this direction, right? So do people need similar nudges, or is this a core part or property of human reasoning? Do we just come with this by default, right? So at the limit, we can give a talk on this topic. We can clearly think in this way, but is this kind of a basic part of how human reasoning works, or does it require certain kinds of augmentation? And then what determines whether people represent the sort of true algorithm, where true algorithm is, in these cases, the sort of ground truth designed by the experimenter, by the problem designer. Okay. Okay. So this work is not by me. The next few experiments is stuff that we did in my lab. I love talking about this because it's such a fascinating, it has a fascinating intellectual history, and the data are also quite compelling. So this is a review paper that summarizes a lot of empirical work by Ed Wasserman and his collaborators. And Ed started this project by working with animals, particularly pigeons. And he was interested in the ability of pigeons to learn this type of distinction, which was thought, since at least William James, to be kind of the core of human categorization, the distinction between sameness and difference. And so in a typical experiment, pigeons would be exposed to displays like this. He started this work in the 80s. These are the old Mac dingbats. These icons, of course, they're meaningless to pigeons. So a pigeon would be presented with a display like this and would be reinforced for picking the correct button. In this case, the button that means same, meaning that all the items in the display are the same, and would be reinforced for picking a different button for a display like this, which is an instance of difference. And the question is, how do they generalize to other instances of sameness and difference, both with other visual icons, but also different amounts of difference, right? So same here means everything is the same. Different is just everything else. Okay, and so you can see how pigeons, after being trained with these kinds of displays, generalize to these. You can quantify the amount of sameness in terms of visual entropy. And what you find is that pigeons are sensitive to sameness, but as you can see, it depends on the degree. So what they do is they generalize based on how much sameness there is. And clearly people wouldn't do anything like that. And so at some point in the late 90s, Ed started running these experiments with people. And the pattern he and his collaborators kept finding over and over is the following. So if you tell people what the rule is, of course they can do it. Oh, same versus different. But you don't tell people because you want to do it in the same way that you do it with pigeons. So you reinforce people in the same way that you do it with pigeons, and you see what they've learned. And what you find is that most people, it ranges from about 60 to 80% across experiments. It does matter, for example, whether the individual visual icons are meaningful or are they just random shapes. But you always get this interesting dichotomous split where most people quite quickly kind of figure out, oh, it's just same versus different. And then they generalize in this dichotomous way. So same is one thing and anything else is different. But a minority, 30% to 20 to 40%, do what the pigeons are doing. This, despite several decades of work, interestingly, it's not only this type of task that has this distinction, but it's not anything obvious. It's not like they're just being lazy or they somehow have lower intelligence, whatever that means. Like they're not different in any obvious ways. Their grades aren't different. Their GPA isn't, like SAT scores, standardized tests. Like it's not anything of the sort. even people who show this categorical distinction between sameness and difference, if you look at their reaction times, they are sensitive to entropy. It's not that they're not. It's just one way of thinking about it is they override it. Okay. Okay, so moving on. Something that we've done a lot in my lab is think about what kinds of tasks become hard when people are partially deprived of language, when language is interfered with, various ways to get at the question of does performance in various tasks somehow recruit language or depend on language? And I saw that Saremi had this same different in the talk, and we happen to have some data that speaks to this. And so some years ago, some collaborators, Martin Zettersten was a grad student in my lab, and Jing Paul was a collaborator that gave us, through whom we got access to this interesting population that I'll describe in a moment, of children who were born deaf. They were living in China in a special boarding school for the deaf. Until they came to the school, they were not exposed, as tragically is still the case for most people born deaf. They were not exposed to a full natural language. They weren't exposed to sign language because no one around them knew any sign. And they weren't exposed to spoken language because they're deaf. And so these are kids ranging in age who have varying amounts of, after coming to the school, of exposure to both Chinese Sign Language and various other methods. They use all kinds of mix of pedagogy, such as lip reading, and of course they're also exposed to written Chinese. So we ran a task of the kind that relational match to sample task is called, the type that's often been used with kids. So kids see a display like this, where they have to pick which one matches the top display, right? And at first they're guessing, but they're getting feedback that's telling them that it's about the relation. So same goes with same, and different goes with different. Okay, so what do we find? So that's the sample. You can see it ranges from age 7 to 20. And it also ranges on the y-axis, the age at which the children were first exposed to Chinese Sign Language. What we find is that performance on this task correlates with age, but not with their chronological age, but with age at which they were exposed to a natural language. And if you look at specifically whether they know any symbolic representation, whether written, spoken, signed, of terms same and different, that's a strong predictor of how well they do on this task. All right, one more example. So this, from Saremi's talk, is an example of a Raven's matrix, now more generally called matrix problem. It's a staple of what are often called fluid reasoning tasks, or also called nonverbal reasoning tasks. And in the literature, people often assume these tasks are what they're called, nonverbal. Why is it nonverbal? Well, because you don't need language to, it was originally called nonverbal because unlike other parts of IQ tests, which is this part of, the task itself is not delivered linguistically. So you don't have to know to read. Also, the stimuli are not words, unlike many other IQ test problems. So that's the reason it was originally called nonverbal, but then people kind of assume that, well, it's nonverbal, it doesn't involve words, so it has nothing to do with language. It doesn't depend on language. So in a series of studies, we looked at this by looking at the role of nameability on people's ability to solve matrix problems. So these matrix problems vary along multiple dimensions. One dimension is how complicated is the underlying rule. And the more complicated the rule, the more steps it takes to solve, right? The harder the problem is. But they also vary, incidentally, in other ways. For example, how difficult it is to describe the individual items. So you can ask people to describe, for example, describe the cell so that it can be distinguished from other cells, and then you can evaluate from simple to more complex measures, how much language does it take? So for example, if the difference, so here's an example of a more nameable problem. Here's an example of a less nameable problem, okay? And we can look at the role of nameability controlling for other factors. And what we find, these are problems that we designed, same logic, where we can keep the logic the same. This is the better illustration of it, right? So here the logic is the same. It's just that these ones use familiar and easy to name shapes, stars and circles and squares. And these are arguably equally discriminable, but harder to name shapes. And these displays are on the screen the whole time, so they don't require remembering these shapes. Okay, control for visual complexity, discriminability. And what we find is that the number of rules plays a role. The more rules, the lower the accuracy. But controlling for it, nameability plays a significant role. It's not a huge effect, but the more nameable, the easier. Why? Because we argue it makes it easier for people to pose and test hypotheses, right? So is it about the square? Is it about adding a square and a circle, right? And if you ask people to reason out loud as they do the task, this is exactly the kind of thing they report doing. This is made harder when you use harder to name shapes, even though the kind of ground truth logic remains the same. Okay. And lastly, I found this really cool, and it, again, raises the question of whether there's any psychological reality to this distinction. So not just, oh, are the ones on the right harder for people? Because there are all sorts of reasons why they might be harder. But what do they require other kinds of things? Like, are they more dependent on the amount of formal education the participants have? Are they more sensitive to being exposed to particular kind of cognitive chunks, right? That people can sort of retrieve and recombine on the fly rather than having to reinvent during the course of solving the problem, which is hugely more difficult. And while it might be achievable for some people, it might not be for most. So that's all I have. Thanks.
Terrific. Thank you.
You don't have the question because when you get I went into
I mean, the questions that are on the other, spectrum. I'll let you do mine. Or do you want to respond to him first, or do you?
Fascinating, I must say. Thanks for doing that. Not sure what I can say, but I knew there were a lot of experiments done like yours, but I didn't really study them. So I think it is definitely a different angle and a very interesting one. I wonder if, I mean, ultimately what I want is to understand what are the biases that humans have that help us solve these problems that we could put into machines.
Right.
And I think you kind of asked the same questions from an empirical study that I think is super interesting. And really like to have your slides at the end.
You'll get them, yeah.
Yes, okay. So let me read the questions from Catherine. It seems as if you're saying that the way people simplify things is very different from how LLMs simplify things. So that's why LLMs have trouble generalizing. Yes, and when I say trouble generalizing, they do generalize. They just don't generalize the way we do. Again, it's more about their priors, and our priors are different. In a way, they are generalizing in some ways. It's just not appropriate. The problem when the kind of problems you look at is underspecified, which is always going to be the case for these reasoning problems. the only way to distinguish two solutions that are compatible with the train set is to have a prior. And the prior that we have in the LLMs seem to be different from the prior that we have in humans. Jane asks why LLMs learn grammar, but not some other symbolic rules. How do these problems and training data differ? I don't know. Maybe someone has a better answer than me to that question. I don't see, like from my vantage point, whether there's something specific with grammar. I think the main problem, I think if everything was specified in training examples, I think it would work well. So that's not the problem. It's not whether it is hard to learn. Most of these LLMs can actually learn by heart all the training examples you're going to see. So they can really understand all the training examples. But then they have to make up their mind about a new example. So did they learn? It's like, think about grammars. There might be more than one grammar that actually embodies the training examples you've seen. Which one it is going to learn, you don't know. So that's the main issue. It's not that they can or cannot learn. They do, but they will have a different prior than we do. Davide asks, can we say that there exists a set of non-computable functions essential for human cognition and the human capacity for reasoning and understanding? Is it thus possible that the mathematics behind large language models cannot reach the same level of reasoning as a human because there are experiences and capacities that, even if they can be formalized, cannot be implemented into a computable function? I would not be as harsh as that. I think these models are, they can learn basically anything, given the size of these models. You wanted to say something?
No, I don't want to interrupt.
Okay, so again, I don't think they cannot learn it. I think they might learn it in a way differently than we do because they start with different priors. I don't think there's anything wrong about being able to do mathematics or reasoning with LLMs. It's more our learning algorithms that should probably be taught again. And in fact, so let me just give you like one recent result from a paper we just submitted, where we use an LLM again to solve a problem. Now, these hard problems, say, let's talk about parity, or let's talk about any problem that is hard. As I said, there are multiple solutions to solve it. And what an LLM does is that it just produces one token, then given that token and the rest, produce a second token, and it produces a sequence that at the end of the day solves the problem. And I talked about these techniques that people use. It's called the scratch pad. It's a way to say, well, don't answer me right away. Don't tell me whether it's parity, yes or no. Show me your work. Try to decompose the problem in a way that will then get to the solution rather than just give me the solution. And these usually succeed far longer, so they can solve problems of longer length much more than if you don't ask the model to try to decompose the problem, to try to reason about the problem. We've seen many papers in the literature. They have multiple names, but they all find this fascinating thing that the LLM, if you ask a question about anything, and you just say, please answer by yes or no, or please just give it as the answer, it's going to fail most of the time. But if you instead push it to reason, to decompose the problem, it will work much more. And we actually showed in the paper why this was the case. You can show that hard problems, if they are decomposed, each of the composing functions of the decomposition, if each of these functions are simpler, then actually the complexity of the whole problem becomes just the max of this small decomposition. So suddenly a problem that was very hard is now just the sum or the max of a sequence of small, simpler problems. And so you've decomposed the hard problem into just simpler problems. You can show that if the model has seen that kind of decomposition in the past, it will do it again, and that will suddenly solve these hard problems. So there's a path. The only thing that we haven't solved, no one, is how do we instill this this process of learning to decompose things. So when you show it to with some examples, you say, well, if you want to solve parity problem, do this like this. You handheld that the model, it will learn it and it will solve it. So that's the good news. LLM can solve this hard problem. But for now, you either need to have shown it before how to decompose, or you need to show it for every single example, which is not practical. So we're not there yet, but we have like a proof of concept, and we have a proof that if you know how to decompose, you can decompose. So that's the answer.
So I wanted to employ.
Well, come on. Come here, so we can.
I wanted to refer to an old concept, which is deuteral learning or second-degree learning. For what I see, isn't it the problem that we don't have a way to teach these language models a way of learning? So teach them how to learn.
Yes.
Certain. This is the crux of the matter in the end.
It's totally the crux of the matter. And in fact, we do with these techniques where instead of just learning, telling them to learn, if this is the input, this is the output. If instead you say, this is the input, and here are the steps to solve it, it will indeed learn the steps. So it will learn it. Now, it will learn it only for problems where it's the same set of steps to solve it. If suddenly it's a different combinations of steps, you're still back to the problem. And that's where we are now struggling, of course. So there's more work to be done. But you're right. Models can learn to decompose if you show them how to.
But they can't generalize.
And then,
the problem.
Well, they will generalize to all the similar problems of decomposition, not a different kind of decomposition. So it's one step in the right direction, but it's still not there. All right, let me move on to Anonymous. Anonymous asks, in the generalization of the unseen work, would pre-training on higher degree function for some problems allow the model to learn higher degree Boolean functions on other problems? I think it's a very interesting question. I think we did some experiments. Trying to remember. I think it does help, not for higher degree, no, for similar degree function. No. Oh, okay. If you pre-train on higher degree, will it work on higher degree? Yes. The answer is it will be easier to learn as usual. And that's compatible with what I just said. If you pre-train with similar problems, it will be more easy to solve a problem of the same category, but not a longer one, a higher degree one, fortunately. Question for Sami again from Anonymous about RASP. Would access to a scratchpad memory allow the transformer to represent more complex function? So I just answered that question from the previous question. So yes, scratchpad are very, very powerful mechanism which gives more memory to the model. Instead of answering right away, it can do partial work and use that partial work to, in the end, answer the question. But it's not any kind of scratchpad. So there are many ways you can implement scratchpad. One of them is just to say, use as many tokens you want to answer. So it's what we call an uninformative scratchpad, where the only thing you say is you can use like a blank sheet of paper and write whatever you want and then answer the question. That doesn't work. If instead you give a scratchpad with instruction, do this, then do that, and you will find the solution. And then the model can actually decompose the problem in doing this and then that, it will find the solution. So scratchpad as such, which is just the ability to have more compute power because you can compute more intermediate symbols before you get to the right symbol. that's not enough. But if it's compute power with guidance about what to do with that compute power, then that works. And depending on the guidance, it will work. And we showed multiple ways of doing this guidance. I won't go into the details, but it can be pretty good. For instance, if the solution you want is to apply some recurrence, so the same decomposition multiple times, if you just show the recurrence, it will actually learn it. So it can be very compact in the scratchpad. And there's a question here. You should come. I can ask.
Yes, come up.
Yeah. Okay.
So I'm just wondering about these emergent properties.
Yeah.
Do you think they really exist? And if they do, how does, relate to the Russell,
I don't think they exist.
Okay.
I think it's no, I mean, it's more about how you talk about them. So there were a couple of papers trying to explain these emergent properties. So backtrack, what is emergent properties? People have observed that as you train bigger and bigger models, from 100 million parameters to 1 billion parameters to 10 billion parameters to 100 billion parameters, on just what LLM is trained on, which is predicting the next token on a huge corpora of text. As you do that, you can see that it's able to solve new tasks that you didn't think it would be able to solve. So you train it on just predicting the next token, but suddenly it's able to solve a translation task from English to French. Suddenly later it's able to solve a summarization task. And these things you've never trained to do it. So that's the emergence property. And there are people who have written a long list of these tasks and try to see what happens. And indeed, as the models become bigger, they are able to solve more of these tasks. People were puzzled. Now, what they were puzzled on is the fact that suddenly, at a given point, they are able to solve a task that right before they were not able. So it just suddenly emerged. Before that, it was not able. Now it is able. So with 100 million, it's not able to solve it. With 1 billion, it is able to solve it. Now, the truth is that it's not like this that it works. It's actually all these tasks, you can measure their performance as you train bigger and bigger model. And they are going to be able to solve, to reach a solution that is more and more near the right solution. So suppose that you're asking a simple task, is the sum of these two numbers bigger than a number? You can, instead of answering yes or no, you can say the probability that it's yes, and that probability will grow slowly to the actual threshold of being more than 50%. So if you look at the probability instead of whether it's bigger than threshold, then that probability always grows. So as the models are trained on more and more data, they are just able indeed to solve more and more of these tasks. More likely because there's more and more examples in the training set that are similar to the questions you're asking. Because as you train on a larger corpus of data, there's one example in that corpus that is similar to the question you just asked. And it's nearer and nearer. So as you go, it is getting nearer to solve the problem. But if your question is yes or no, it looks like suddenly it's yes, and the day before it was no, just because you just cross a threshold. It's a nonlinearity that is arbitrary. That doesn't mean anything. The model is just slightly better than yesterday, or slightly better than the smaller model, just because it was trained with slightly more data. As you train with more and more data, you are more and more near any question you're going to ask. And that's the real explanation of what's going on.
Okay, so no emergent property.
Not in the sense of suddenly it's better. Yes.
Is the Q&A refreshed?
Well, there's still plenty.
Yes, you have plenty of time.
Okay. Okay, that was for well, so the question that was asked about the scratchpad is, if you have access to scratchpad memory, will you be able to represent more complex function? And as I said, depending on the kind of scratchpad, the answer is yes. But for just the memory, the answer is no. So if you just say, you can have this blank sheet of paper, can you do something with it? It's not going to help, unfortunately. Sarah is saying, I asked ChatGPT-4 about parity. at first it said wrongly, and when I said it's wrong, it wrote a Python code for it and answered correctly. Ooh, that's cool. Yes, that's true. Do you think that it will be possible that they just start coding for everything? Also, isn't coding understanding the problem? Does it mean that they understand the question and just don't know how to do that? So that's a very interesting thing. First, there are many things to say about this. First of all, parity is definitely a problem that exists. I didn't make that problem. It exists. You can find code about it. You can find people talking about parity on internet. And so GPT-4 has been trained on parity. It's not something new for it. It has seen numerous examples of code writing parity problem. It's not something new. So can it write code about parity? Yes, because it has like hundreds of code versions of parity that exist. So it's very easy for it to learn to write code for this problem because it saw it already. There's nothing new about that problem. So the real problem now is to think about a problem that is not on the internet and for which you can ask the question. So parity here will be much too easy because everybody talks about parity on the internet. So it's a very well known. And these large language models are trained on everything they find on the internet. So again, they learned everything by heart. Coding parity is actually a very simple program. You can see it in many ways. So did it actually understand parity? I don't think so. It understood that what you're looking for is the program for parity, and it can show it to you. That's a very different question. Fortunately. And people have tried this kind of trick. For instance, so there's this colleague was telling me about this, the Monty Hall problem. I don't know if you know this. It's a very well-known problem.
So explain it.
Okay. So the Monty Hall problem is the following problem. We have time?
Yes, yes.
All right. You're confronted to a problem where there are 3 doors, and you have to pick one of them. One of them has I don't know, a big, a brand new car behind it, and the 2 others are gonna die or something bad happen. So I'm asking you, okay, which of the doors you will pick? You pick one, you have no prior, there's no reason you would pick any other one. And then, that's the then that is interesting. Then I open one of the 2 other doors. So you picked, say, the first one, and I open the second one, and I show you, it's not behind that second door.
You have to say importantly, you know where it is.
Of course.
And you will not open a door where it is.
Yes. Right. Of course. I didn't do it randomly. I know where it is. You asked me to open the first one. I say, well, wait a minute. I'm going to show you it's not behind the second one. And then I ask you, do you want to change your mind? You want to stick to the first one or go to the third one? Given that I opened the second one, you wouldn't. Okay, so that's an interesting conditional probability problem that everybody studies at school, and everybody knows how to solve it. We're not going to go into the details. If you ask ChatGPT to solve it, it's going to solve it like hands down, no problem. Why? Because it's on the internet, because you can see numerous versions of this. Now, if you change the question slightly, for instance, indeed, you know where the thing is. So suppose it's behind door 2, you say door 1. Now, I know where it is. I am now going to tell you, I opened the second door and the car is behind it. Do you want to change your mind? And it will fail the problem, even though I told the model, here's the solution. It will fail it because the problem is never asked like that, of course, because it would be a dumb problem. So it learned the Monty Hall as a hard problem, but that's this unique hard problem. Any problem around it, it has not seen it. Any transformation of that problem, it has not seen it, and it's going to fail it. Did it understand the problem? I don't think so.
And your method, how would your method cure it?
No. I'm not saying I cure everything.
No. The one that worked.
Oh,
you have to train.
Oh, if you try to do it, then it might make it easier. Yes. So it's likely that there's a scratch pad, an informed scratch pad that can help to solve it by saying, well, you know that when you choose the first one, you had a probability of 1/3. think about what's the priority of the second one and then answer the question, something like that.
Okay, relax. This is going so well that I'm going to use executive to continue the discussion to almost the next speaker. So do as many as these.
Okay. Whatever. All right. Let's move on to Armin. Armin is asking, I didn't understand how you determine that the Rasp language is one of the transformers should be able to implement in order to solve the problem. So we, as I said, we actually don't have a proof that this is the case. It's only a conjecture that if there is a Rasp solution to the problem, then the transformer will learn it. We only did it experimentally. We don't have any way to prove that that's the case, unfortunately. And what we know is that, well, this Rasp is interesting, is that this Rasp language, if you can write the code in this Rasp language, you can actually find the parameters of the transformer that implements that code. So it's not just that you can learn it. You can precisely write the parameters of the transformer that implements that. So that we know, that was proven like in 2021. What our conjecture is, not only it exists, but it's what it is learned. And that's what we showed empirically. Theo is saying, regarding bias and priors, could you get them by real world experience? Why try to solve something in theory if it may turn out that you can only get your answer by confronting the world? Try and error learning in the real world. Do you consider solutions of that kind? So that's the grounding question. You said, exactly. I hope you're going to talk about grounding. I didn't, but Theo did. Yes, there's a lot of people saying that you will never be able to solve interesting hard problems of interest to humans if your model is not grounded in the real world. Grounded just means in this case that it's going to be exposed to the world in many ways similar to what we are. So we experience the world through senses, vision, touches, smell, whatever your senses are. And these LLMs, they experience the world through text only. They don't have any vision. They don't have any other sense. They don't see an apple falling in the tree. They don't see someone coming to you. They don't experience the world like you. And the question is, maybe if they were grounded, maybe if they were seeing the world or experiencing the world as we do, they would get these things. It's possible. Definitely, there's a lot of people interested in that area. There's a lot of, for instance, there's a lot of work in these vision language models. So it's already adding one dimension, but it's still not like an object that would be put in the middle of a classroom and then would wander around and ask questions, touch the thing by itself. I think we're not there yet, but there's good reasons to think that it's a good way to go. It's just not efficient. Train these models on billions of learning examples very efficiently. So these LLMs are trained on data that you will never see in your whole life. So a quantity of data that is just crazy. If we had a machine that can experience the world, it would be as slow as we are all. So it might not be efficient to do these experiments. So hopefully we'll find a way to be more efficient. But today, that's the reason why branding.
As slow as we are from zero, yes, but not from today.
Absolutely, yes. But if we had to start from scratch, that's hard. Is it possible, Ali is asking, is it possible to minimize the LLM biases 100%? I am not sure I understand that question. It is possible that the LLM learns by heart everything. So if that was the question, yes. LLMs have biases. We all have biases. Every learning machine has a bias. It is used to complement the training example that it sees. For humans, it might be based on the genetic or your whatever genes you have or any approach like that. For machines, it can be priors that come from the learning algorithm. Usually it will have some kind of reducing the weights to 0 or something like that. Some prior that says if you have two functions, which one will you choose? So all models that learn, all machines that learn have priors. And it's good. The question is to find the right ones, not to remove them. Anna asks, maybe a naive question? Certainly not. If you post-treat a transformer with reinforcement learning, as it is often done, is it conceivable that it changes its original neural architecture so that it becomes more similar to the human way of generalizing, and you can make it forget its original priors? So I will answer the last part, make it forget its original priors. Yes, learning is always going to be a gentle combination of prior and posterior. Prior is everything you see the world before you see any example. Posterior is how you will change now your parameters given what you've seen in the world. And so you have both. You have priors and posteriors. Every time you see a new examples that tells you how to change your parameters, you're slightly changing your biases from more of the prior to more of the posterior. So now she's asking about techniques that are called like human feedback reinforcement learning, or reinforcement learning with human feedback, RLHF, where after you've trained these LLMs, you show the LLM examples of the form, for this question, humans prefer that answer to this answer. And you will show a lot of this kind of preprint. For this question, humans prefer answer A to answer B. That's the human feedback. And you use reinforcement learning to train that. No reason to go into that details. It's hard, but it is not that good. It is going to be very pointy. It will try to do the same thing as those humans for these questions and questions similar to those, but it's going to be very narrow. So for any other question that is so far from the questions you showed it will probably not work well. It will do what we call overfitting. Will be very good on all the pairs of examples you showed it during that part of training. So that's not very satisfying. We haven't found a good way to do RLHF in a way that generalizes to other very far away pairs of examples. So it does remove the priors, but only around these questions that were shown during RLHF, fortunately. Ali is asking again, that's the one who asked whether the biases are minimized 100%. He says, if LLM biased minimized, can LLM reason like humans? I think the answer is the same. It's not that they should be minimized. I think they should be changed. We should try to find biases, priors, that are more aligned with what humans do. And in a way, that's what people were trying with these RLHF. And people often call that the alignment problem, where they say, well, there are many answers to questions. We want the model to answer something that is aligned with the values of humans. Do good, don't kill, whatever. And that's what we try to teach the model with these post-training approaches. So it's not like you're minimizing the biases, you're changing them towards what we humans as a community would prefer a model to say. But it's not working as well as we'd like, unfortunately. And also maybe your values are different than their values, and that's we're entering a difficult place. Vishnu is asking how the trained data is stored internally, whether it is algorithmically or in form of binary bits of or any other representation. So an LLM is, as I said, a transformer. A transformer is a very specific kind of neural network, and a neural network is basically only meant to be a collection of weights and biases or parameters, and these parameters are real valued numbers, and usually they are of the form, you do the weighted sum of terms, and you pass it through some nonlinearity. If it's higher than some number, then this happens or that happens. That's the only thing that is in a neural network. So are they stored? They are stored internally in terms of real numbers. Of course, because it's a machine, not really real. It's quantized in a way. It could be each number is represented in 16 bits or 32 bits or 8 bits, depending on the kind of memory you have. But there's a representation. This is more of a computer science question. So at the end of the day, you're asking, are they binary bits? Yes. At the end of the day, in a computer, everything is binary. Everything is bits. There's nothing else. But it's not a very satisfying question, but sorry, it sounds like that. But with binary representation, you can represent a lot of things. So it's not too much of a concern. Matthew is asking a broader question. Humans are often used as a reference point for understanding generalization in AI/ML models. Do you think the field might be overestimating the degree of which humans are novel in their generalization? Well, the problem is what we want to do with these LLMs, I think. It's more that when people think of these LLMs, they actually have, humans have priors about what they expect from these machines. They expect these machines to answer as humans. And they are amazed when they do, and they are scandalized when they don't. But it's the expectations of the humans. The model just learned to predict the next token. There's no magic here. The model is only predicting the next token with some biases. But we humans, we maybe anthropomorphize and we say, oh, this machine is generalizing, is a human, is intelligent. Use the term you want. It's only predicting the next token. There's no magic behind it. Exactly. Yes, Gary.
Camera.
Yes.
I think that's a really important question to ask, and to there are many a Twitter thread where people are talking past one another because one person is thinking of LLMs as a sort of production system that should have sound reasoning and provably correct, and another person is interested in the kinds of things that don't have ground truth, right? Here's an open-ended question. What I care about is whether it gives me a satisfying answer that's not obviously false, but like, who's to judge what's true? And those are very, very different kinds of tasks. And there are lots of domains where when we interact with machines, right, we don't want them to be human-like, right? If you want to turn on the windshield wipers in your car, you want to, push a lever and have it turn on. You don't want a language system that, is trying to interpret what you might mean in that context and asks you, can you say like the way a person would, right? Might not hear you right, ask you to repeat yourself, right? And so I think, yeah, as a field, like we all need to be clearer about what the use case is. Are we thinking of it as a cognitive model? Are we thinking of it as a way of better understanding human function? Or do we just care about deploying it and having it, be a reliable tool?
Yeah, I agree with you. I think there's a wide variety of what people want from these models, what people expect, what people think they are doing. They are only doing one thing. Again, it's predicting the next token. The question is whether it's useful, whether we can use that prediction of the next token to solve an interesting task. And then, so that's my view of, I'm just a computer scientist. I want to solve the task. Can this thing solve the task? That's what I'm asking. Of course, plenty of other people have very different questions. People may want to say, well, this looks like it reasons like a human. Maybe it can help us understanding how humans reason. And maybe I don't know, but it's an interesting question. That's not the one I've been trying to answer, but there's plenty of interesting questions like that. As long as we all understand that this is not a human, it is just a machine, and we pretty much understand how it is trained. We don't necessarily understand to which extent it will be working well on new problems, and that's the questions we're trying to answer. But a lot of people see more than what we should. They want to see things that they haven't seen. They want to think that it's intelligent. was not being defined. And I think we have to be very careful with this. It is, there are debates about that, and people are, concerned about things that they should definitely, but they're also concerned about things that they shouldn't, just because they don't understand what's happening. So lots of debate to come.
Are you exhausted?
No, never. But when you are, you're not. Okay. Anna is asking, can you hypothesize from an output of an LLM whether the performance is an effect of the supervised learning, the pre-training, or an effect of later tweaking methods? It's not easy to answer. So, these LLMs are trained in multiple stages. The first stage is just predicting the next token. The second one could be to do the same thing, but for a very narrow task. So you want to be good on that task. That's called fine-tuning. And then another one can be what we call the RLHF, trying to say, well, if you have to answer and there are many options, pick this one rather than that one. So that's the alignment with values or with humans. At the end of the day, do you know when the model answers whether it is coming from the pre-training phase, from the fine-tuning phase for the RLHF? I don't think we have studied that as far as I know. So I don't think we know. One thing that I would like people to study more is more related to this notion of hallucinations. You've seen that people use this term in the common language, that these models are hallucinating. And what they mean is that the model is basically saying false things. But it seems to be more trendy to say hallucinating than just saying it's false. And the question is, can we detect whether a model is saying something false? That would be very useful. And more generally, can we calibrate what the model is saying? And by calibrate, I mean, when it says something, can you compute the probability that what it said was true? And if that probability is high, you can believe it. If it's low, you may want to set it aside. And that would help you being able to combine two things, for instance, two things that have low probability. When you multiply them, it's going to be false with high probability. But we don't know how to do that well. That's an open question. And that would be very useful if we knew how to. Stefan says, you seem to imply that the LLMs don't generalize, but rather do a similar association with nearby examples. In the 70s, we referred to this exemplar-based learning versus prototype learning. If this is what you're claiming, it seems contrary to the generalized structures in the attention head that represent various circuits, sort, move, etc. that seem to be general operations found by Anthropic or other researchers like L, Pavlik, etc. How do you square these ideas with the attention head circuit data mining? I think these are not pretty antagonist. What one says it's an exemplar, the other one would say it's a prototype. It all depends on where you look at. I think a model like the DeepNet takes an input, transforms it into another representation, then transforms it into another representation, and does that in multiple stages. And if you look at the last stage, the only thing that this model will do is do a nearest neighbor in that last stage. So a nearest neighbor is just look at something that is near in that space. And yes, you can show that after transformations, even the more complex rule that you were thinking of will be just at the end of the transformation, a nearest neighbor in some space. So it all depends on which space you're looking at to define whether it's a nearby exemplar or it's a prototype. Both are the same thing, just in different spaces. And I don't think they are different. It's just a degree to which they are doing one or the other. So I don't think it changes anything. It's sadly, I think people often say, well, my model is just memorizing, it's not generalizing. This is not, again, a dichotomy. Models that are good at generalizing, they also memorize well. And then we had a paper many years ago showing, indeed, that memorization not only is important, it's actually happening in good models, and it's very important. So memorization, generalization is not one or the other. You actually want both at the right time. And that's pretty much what these models are doing. Anna is saying, in other words, how can you prove that your fine-tuning really made a difference? Well, that's so we are back to Anna was asking whether the answer you get is because of fine-tuning or pre-training. And the only thing you cannot prove, the only thing you can say is now on examples that are similar to the one you asked, it's getting better. So you can measure with the test set whether it's getting better. And that's going to show that your fine-tuning was worthy of doing. Hamid says, as many of us are intrigued and eager to advance various facets of LLMs, where is the line of the concerns and precautions associated with LLMs, as well as to have regulations related? Ooh, that's a loaded question. But let's see. As these models get more powerful, or appear to be more powerful, they can do a lot of things that are very useful. But at the same time, like any tool, they can also do things that can be dangerous. Just because it's a more powerful tool means that they can be used in bad ways as well as in good ways. Where do you draw the line? Should we have regulations that say, well, your model should not do this, or we shouldn't have models that can do that? I think we should. I think this is important. I think
you said or, and you said yes to or. Which of the ors do you mean?
Oh, I mean, we should have regulations. I think it's independent of the fact that we should keep working on understanding what they do. We should also make sure that they do good for our societies as large. It doesn't mean that today we should stop everything. I think we should educate the people. We should educate the lawmakers. We should educate those who understand or need to understand how society will be changed with these models. That's necessary. There's no, I don't think anyone disagree with that. The question is now to which degree it could be enforced into blocking you to do this, or blocking you to do that research, or blocking you to publish your model. There are plenty of things where regulation could happen. And I think each society should think about what that means. Maybe there should be something more global. I am definitely I agree that we should definitely think about that and have the best for our society. We should not let it go unregulated, but that doesn't mean stopping everything. That means doing what we do now, which is trying to understand what they do, and maybe stopping the things that are dangerous when we understand. Today, we don't really understand much. We don't really understand why a model suddenly is able to do this and not that. There's still a lot to do, so we're not going to stop it until we understand which ones we should stop and why. We should definitely regulate. And Anonymous says, assuming that we could put the whole training data from an LLM into a vector database and do retrieval augmented generation with it, would we find out why an LLM is hallucinating? So this retrieval augmented generation, in case it has not been explained before, it's the idea that an LLM has been trained on some data and is able to reason about that data in a way. That's what the LLM does. But you could think that there is separate from the LLM a database of facts. Barack Obama was born in this country. The Prime Minister of Canada is this person, at least at that date. And these facts can change. Of course, Prime Minister of Canada can change in 5 years. It might not be the same as 5 years ago. And so these facts are evolving, while your LLM might be fixed and trained on some data that you've seen at some given day. So many people said, well, we can do this in 2 stages. We can use the LLM as a way to use language, because language is hard to get, but with a lot of data, we're able to have language. But the facts should come from something that evolves separately, from a database that is updated as soon as the new facts arrive or a fact is changed. So that's the promise of this retrieval augmented method, where when there is a question, the first thing that the model does is go onto that database or search or anything, retrieve relevant facts, put it in the context of the LLM, and then ask the question, given the fact that Obama was born in Hawaii and that Justin Trudeau was Prime Minister from that day to that day, tell me today who's the Prime Minister of Canada. So suddenly you have the fact, you can use it, and it's easier. Of course, that's a promise. It works sometimes, it doesn't work. It depends on how you retrieve, which facts you retrieve. How do you know which fact to retrieve, whether the facts are updated? And also, as the context gets longer, LLMs are less and less good at actually using any needle in the stack of your context. So the context might have like a million token, which is very a lot, but only 20 tokens are important for the question. So how do you make that work? It's still an open question. So that's a good approach, but it's still research. And believe it or not,
You did.
there's no more.
Bravo.
No one cares.
Fantastic. I'll give you one last one. In another direction, we have computer scientists here, and we have psychologists and neuroscientists. And as Gary said, their motivations are somewhat different. There was something that you said about, in the end, about strategy of using the LLM, the one where you said break it into, you repeat the thing and break it into chunks. It strikes me, and I'm a human subject in this. I use ChatGPT a lot, and I feel that compared to last year, I am much better at it because it has been training me on how to use it.
Absolutely.
Are there any generalizations to be drawn?
Well, first, this is not new. I worked for Google for like 14 years. And it studied how people answer a query on Google search. And 10 years ago, the queries had an average length of 2.3 words. The queries were very simple. Say 2 words or 3 words, and you would get answers. And as the models got better, as the humans got better at asking the questions, their queries got longer. And they were able to express things that are more nuanced and get answers that are more precise. I think it's been a joint effort between those search engine and the humans using it to actually focus on what works. And it's the same for ChatGPT. And in both cases, the data is used. Every time you ask a question to Google, first the question is scanned, as well as the answer. Every time you ask a question to ChatGPT, of course, OpenAI keeps the question and the answer, and it will add it to the database of. So it is a joint effort.
It's not just length of question that's an issue, but also what series, how you chunk up your.
But of course, back then in Google, it was a single question and simple. Now it's a sequence of questions, much better.
With that, I want to thank you. The Bengio family is definitely leading us into the future in this. Thank you very much.